Hello, today I'll be demonstrating our senior design capstone project, Hammerhead Autonomous Marine Rover. So, I will go into a bit of the architecture. We have our first main MCU, and then we have our gateway buoy. I will also attach a system block diagram to give a better idea on how everything is structured and a reference throughout the whole video. Hammer's propulsion system begins with a 1500 kilovolt brushless motor, which is attached to a 30 amp ESC. In addition, we have three 20 kilogram servo motors that ran on 6 volts. Then we have our main MCU, which is an NVIDIA Jetson Orin Nano developer kit. This MCU was chosen in particular for its GPU computational power, specifically using CUDA, which is utilized by the Z camera for its depth perception and mesh mapping. In addition to this, we also had prior experience, particularly George Babick, as he's taken an edge computing class with the Jetson Orin. So shout out George for helping us with that. Our gateway buoy consists of a TP-Link portable router and a 4S 9000 mAh battery. The reason why we chose the gateway buoy design was that initially we wanted to use an acoustic modem, which would allow us to communicate underwater wirelessly. However, this came with a big price tag. By using the gateway buoy, this would reduce the cost significantly. This would still allow us to have wireless connectivity between our laptop and Hammer itself via this buoy, hence it's called the gateway buoy. This came with its own challenges. I was not able to print the buoy as one whole part as my build volume on my printer did not allow it. This wasn't a big issue though, since we didn't have enough time to test out in water anyway, so it was okay. We will now start demoing the propulsion system, starting out with the motor at 35%. Here it is running at 70%. Keeping it at 70% maximum capacity was ideal, since anything higher than that would take up too much current and it was unnecessary. Next I will be demonstrating the control system, and I have my partner George controlling it from his computer via Foxglove. So here it is turning left, and then here's right, and going back center. Here's a visual representation of the UI on Foxglove. As you can see, there's different plot diagrams for sensory data and motor data. So there's throttle, there's also our rudders, top, left, right, roll, pitch, and yaw, and then we also have pressure and temperature. Here's a recording on George's end as he first hits 35%, and you see the throttle goes up for 35%. Then he'll go and hit 70%, and you'll see that the throttle on the plot diagram increases much higher. As George also hits the left and right rudders, you can see that the plot diagram for the rudders changes as well. So we hit left again, and you'll hit right, and it fluctuates up and down depending on which way the rudders are oriented. In addition, we can also hit center to center back to its default position. Here's another clip showing all of this happening in real life. So this angle that I'm showing shows that no one is controlling the Jetson manually. It's accessed via SSH on George's laptop, which he's able to control on Foxglove. The only thing that's connected to Hammer is the power line, Ethernet, and the USB cables that connect to the Jetson from the Arduinos. And finally, we'll be showing the control system and PID control, starting with the pitch.
Go.
Then we do the yaw.
Don't drop the Jetson, okay?
And then finally roll. For demonstration purposes, we will skip over the electronics and go straight to the perception hole. This hole is responsible for having the sonars and Z camera in addition to the Jetson itself. The camera previously mentioned is the Z camera from Stereolabs. This camera was manufactured in 2015, is discontinued now, but you can find it on eBay for about $100. Here's a demonstration of the Z camera working. On the left hand side, there is a live video feed, and below that video feed, there's colors that represent how far an object is. The cooler it is, the further it is, and the hotter it is, the closer it is. On the right hand side, it makes a mesh map or point cloud of the whole area that it scans. In this demonstration, we decided to make a lawnmower type of scanning navigation. This is important because if we want to go over a certain object, we want to make sure that we get it multiple times so we ensure that it gets a full coverage and it actually maps out. This is often referred to as overlap. Finally, our result leaves us with a point cloud that we can visually analyze and export to other software such as ArcGIS for further processing. This will allow us to see any anomalies, further inspection, depending on the application needed. It also shows us our navigation path that we took. Despite not being able to test underwater, we're still really proud of what we got. So we have all of our electronics working, our main motor, our rudders, PID system, our telemetry, our wireless network, and our depth mapping. That all works. So we achieved what we intended to. However, there are tweaks, there are flaws that will be developed and corrected in the future if we plan to do so. But if you don't want to wait for us to do it, you can do it yourself. All of this will be available in open source. It was intended for that purpose. It's modular, so you can change it however you like. You can change the code however you like. The UI, you can control this with an Xbox controller. You can control it with an air fryer. I don't give a damn. Please like this video. We put a lot of sacrifice, blood, sweat, and tears into this, into making it possible. And yeah, thank you again to everybody that helped, especially George Babick, Shay, and my girlfriend. Couldn't have done it without you guys. Thank you again. Bye.